So this is going to be, I guess, part 2 of me bumbling my way down the dark alley that is perspective projection, the math behind perspective projection. So remember where we left off was that we had found that x sub p equals negative y sub e over z sub e times n, and a similar thing for y sub p. It's negative x sub e over z sub e times n. And we determined that, okay, that means, hey, let's acknowledge the fact that z sub e is being used to divide in both situations. So that means at some point we'll need to do perspective division, which again, this is kind of hard to understand because the only reason I know perspective division is necessary is because I know that's part of the process. Therefore, I'm like, oh yeah, I recognize that. I don't know exactly how you would determine this naturally. I don't know if you're supposed to. I mean, obviously you're not supposed to. You're not supposed to derive every mathematical formula that you need to work with. It's why we have math textbooks and things. But I don't know. I guess I'm trying to formulate how the understanding is all supposed to come into play. But either way, what this kind of translated to, my pen is really kind of messed up. What this translated to is saying we know that the fourth row of the matrix is 0, 0, z sub e, 0, because the way this works then, just the way matrix math works, and again this is a refresh from the part 1 of the video, I cannot write a W. Okay, whatever. The way this works is we'll take this, multiply by this, which means the 0 will go here, the second 0 will go here, this will not be z sub e, sorry. This will be 1, because we want to bring the z sub e through, times 1, and then times 0, which would be 0 plus 0 plus z plus 0 equals z, which means in the final result the w would be our z sub e. Alright, that's the idea. Cool. Where do we go from here then? So the next step is to think about, what are we trying to do with this whole process again? Well, what we're trying to do here is convert from I space to projection space. Is this laid out differently? This seems different. Hold on, it is. Oh, I'm finding a different reference document. Okay, that's the one I'm familiar with. Cool. So something that we're doing here is we're actually going to be taking our I space vertex, multiplying it by the matrix. That's the projection matrix, right? M sub projection times I, which just represents, some 4D vector of x, y, z, w. And this will yield actually our clip space coordinates. Right, I guess something to think about is, see, I don't have a great understanding yet of the different spaces. I know there's I space, clip space, projection, normalized device coordinates. I still don't have a great idea of how those actually lay out one after the other. I just have a kind of ambiguous, abstract idea. But the way this document is laying it out, it's saying the projection matrix times the I space coordinates yields our clip space coordinates. And then we use clip space with perspective divide to then get our normalized device coordinates. And I guess that makes sense that this is kind of the final with an asterisk kind of state or format of our points. But something to recognize is that this process right here is done via perspective divide, which is why we keep that z coordinate in the w spot, so we can use that for perspective division, and that's cool. But then that means we need to figure out, hey, how do we get the, I guess it's just, yeah, it's still not super clear to me, but I can follow along with the math well enough, so let's just do that. Not the greatest explanation, but again, I'm just kind of sandboxing here. So we kind of want to figure out the mathematical intuition behind converting from our, because we now have our, we're able to find our projection coordinates, right? So how do we get from projection to normalized device coordinates? Well, let's think about it. What range is our perspective, or is our projected coordinates in? You know, if we were talking about that viewing frustum, which is then going to be, I can't really draw 3D, but I can show you the diagram here, which again I showed in part 1. This whole thing, this is our, you know, our projection kind of format. This is our normalized device coordinates format. So what is the range here? Well, you can see there's all these L, T, N, F, B, right? You have left, right, top, bottom, near, far. That's the ranges. Over here, it's all a bunch of variants of 1, whether it's -1 or +1. So what that means is, that we're really saying our projection coordinates, so let's just call it P, is going to be in the range, I don't really want an equal sign there, but it's going to be in the range of, well, I guess more specifically, our x sub P is going to be in the range of left to right, because that's the range of our kind of our viewing frustum. And we want to convert this to x sub n, which is normalized device coordinates, which is going to be in the range of -1 to 1. And then for y, it's a similar thing, except instead of left to right, it's bottom to top. And then y sub n is again -1 to 1. And that makes sense. So now we want to use these, because what these really are, you know, let's just do one at a time. Let's just focus on x, and we'll bring y back into it later. Let's also get rid of this just so we can keep it nice and clean. I'm just going to rewrite this up there. So x sub p, again, was in the range of left to right. Convert it to normalized device coordinate range, -1 to 1. How do we do this? Well, what we're really saying here is that this is a point, and this is a point. These points exist on the same line. If you think about a graph, we have a point here. How does that work again? Yeah, you have a linear relationship. Really, I think I was wrong about that. This is not a point. This is not a point, but the combination of the two is a point. What I mean is this left, essentially left -1 is a point, and then right 1 is a point. Because there exists a map, because we know for the projection kind of area and the normalized device coordinate area, we know that the far left range is left, whatever value that is. Far right range is right, whatever that is. And this might be like 0, this might be like 1920, or whatever it might be. You know, who knows? That doesn't have to be resolution. I guess I don't know why I picked that. And over here is -1 to 1. So we know that L maps to -1. We know that right maps to 1. We know that some value in the middle is going to map to some value over here. Now, it's in the same position visually and intuitively, but because the range, the upper and lower values are different, this values might be, you know, -0.75. And over here, well, if this is -500 and this is +500, then this value might be you know, negative 400. Like, we don't know what it actually is. They don't map. They map one to one, but the numbers obviously are not going to be the same. So all that is a linear relationship, which means we would have a line that looks, you know, something like this maybe, where the vertical axis is x of n, which, you know, is positive 1 down to negative 1, and then the horizontal axis is x of p, where, you know, over here is L and over here is R. It's a line, right? It's a mapping between these values to these values, and we can use these two pairs of values as a way to calculate what the actual equation of this line is. So the way we do that is to use good old y equals mx plus b. Now in this case, we don't actually have y and x necessarily. We actually have, well, let's think about this. For a normal line equation, if you're graphing a line, you know, and if you're saying, all right, I have the x value of 3, we'd say, okay, here, and we have whatever equation it might be like y equals 1/2 x plus 3. You'd say, all right, let's just draw these numbers, and we'd say, all right, I want to figure out where this line goes if I have, or where this point goes if I'm using the value of 3. So we'd say, okay, y equals 1/2 times my value plus b plus 3. Say y equals 1.5 plus 3, y equals 4.5. So you'd say, okay, if I have an x value of 3, then my y value is 4.5. And you do that, and you do that however many times, whatever the line ends up being. You go, okay, this is my line. That's how line equation works. Similar thing here, but remember we're mapping from projection to normalized device coordinates, which means our y is actually our output, which is x of n. Our x is actually our input, just a projected x. And b is still b, but let's just, I don't remember why the documents use beta. Doesn't really matter. It's some symbol. And we want to figure out what is the actual equation. We want to figure out, we want it to be some equation where we can plug in this value and get this value. So we need to figure out what m and beta are. So m is easy to figure out if we already have these pairs, right? Because the equation for the slope of a line is the y minus y over the x minus x. So if we do that, remember these are the points we're actually using. These are the actual points on the line. So we'd use those values. We'd say, okay, let's just do this minus this minus this. Okay? So 1 minus negative 1 over r minus l, which is 2 over r minus l. Okay, cool. So we determine our slope. But now we want to figure out our beta, right, this guy right here. So let's plug in what we have. Well, we can just use one of these points. Let's just use this point because it seems simpler. And we know that this is x of p, x of n. We'd say 1 equals, and we have our m as well, 2 over r minus l times x of p r plus beta. And let's just try to work through this and solve this and see where we end up to try to get beta on a side by itself. Well, that's pretty easy here. We can just subtract this whole entire thing here. So it'd be 1 minus 2 over r minus l times r equals beta. Okay, cool. So we then have found another part of our equation. Awesome. But the real hard thing is figuring out, okay, what do we actually want our kind of equation to boil down to? You know, when you're trying to derive a math equation, you don't really know what format it should be in, because you could rearrange this 16 different ways, you know. So I'm kind of just referring to the reference document because, again, I don't have a total understanding of this. Let's just try to simplify this again. Again, I'm trying to just kind of following the reference doc. Let's simplify B, or beta. Let's simplify this a little bit. Multiply R onto the 2 would be 1 minus 2R minus R minus L. Then let's use the common denominator here. So we multiply that 1 by R minus L. So we get R minus L over R minus L minus 2R R minus L, which would be R minus 2R, which would be negative R minus L over R minus L, which really would be negative R minus L. Like, I forget what form it needs to be in. Yeah, you can factor out the negative, so you have negative R plus L over R minus L. And that's going to be kind of our improved value for beta. So let's actually replace that value there with that. And this just makes a little bit of the math later easier, having in this kind of format. It's, again, equivalent to what we had before. Just helps a little bit. Okay, so then we know our equation for our line is going to be x sub n equals 2r minus l times x sub p plus b, which would be minus r plus l over r minus l. Okay, that's the equation for x sub n. Let's write that down up here, just so we have that, because we're going to need to clear some of this out. Let's do the similar thing, the similar process for y. So we actually know this is different. We know that it's y sub p is in the range of bottom to top. This maps to y sub n, the range of negative 1 to 1. So again, we know these points on this line that represent this kind of mapping, this linear relationship, is going to be b negative 1 and then t1. So we have that equation of y equals mx plus b, but where y in this case is actually the normalized device coordinate value. So it would be y sub n equals mx, where x is actually y sub p plus beta m. Okay, let's find that real quick, which was y minus y over x minus x equals 2 over t minus b. Let's write that down up here so we have it for reference. Cool. So let's plug that in as well as one of these points to figure out what the value of beta is. Let's just use this one because it seems simpler because there's no negative. 1 equals 2 over t minus b times t plus beta. Subtract all this again would be 1 minus 2 t minus b times t equals beta. And like last time, that's a really weird beta. Like last time, let's simplify this a little bit. So I really shouldn't even be writing it down right here, but whatever. Let's simplify this a little bit. Okay, let's multiply in that t. And let's find the common denominator right here. So that would be t minus b over t minus b minus 2t over t minus b should equal t minus negative 2 would be negative t minus b over t minus b, which would really be, I believe, is it like b plus t? No, we factor out the negatives, right? It should be negative t plus b over t minus b. Let's rewrite that up here. Cool. So we have that now, and then our overall equation for x, so y sub n, it's very similar. Slope is 2 over t minus b times y sub p minus, now that's a horrible t. Cool. So now that we have that, what do we do with it? So we actually want to use these values, because now that we have x sub n and y sub n, we can use our previous found equations, which, if you remember, was the values of x sub p and y sub p, which are the values over here, which are the values that we would need to find the normalized device coordinates. And remember, the right, left, top, and bottom, those are kind of given to us at the beginning of this entire process when you're actually doing it in the code. So I'm going to write down what those x sub p and everything was from before. And I'm going to write it the way it's actually written in the documents, which just has a negative on the bottom instead. Again, it's equivalent, but I actually might have written them down incorrectly at the beginning of this video, but we have them correct now. Okay. So now we have those. Let's use those and plug them into our equations over here. So let's do x first. So we'd say just kind of rewrite it, but plug in for x sub p what we have here. And this gets a little hairy, so let's hope we can get through it. Okay, and again, this is x sub n equals all that. What we want to do, again, if we think about it, we want perspective division to kind of make its way through, so we want to try to get stuff over z sub e. That's one thing to focus on. Another thing to focus on is to get things timed x, y, or z sub e so that it can be put into the matrix multiplication, or the multiplication, excuse me, the projection matrix correctly. Because if you have some value of, like, let's just say arbitrary numbers like 3 times x sub e plus 4 times z sub e, this can be translated really easily into a matrix row, right? Because we know if you're multiplying this by a 4D vector that looks like this, then if we want x sub e to be multiplied by 3, we put 3 right here, right? Y sub e is this column, z sub e is this column, w sub e is this column. So we'd say, okay, x sub e, 3, cool. There's no y, so we can do 0. There's 4 here and 0. And that equation can then be kind of translated into a matrix row. So let's kind of keep that in mind here when we're thinking about what kind of form, how do we want to reshape this equation that we're working on at the top here. We want it in some sort of form where it can be translated into a matrix row. Okay, so with that being said, and again, I don't know if I'm not a math person, so I couldn't necessarily intuitively figure out the right way to do this. It's more of having seen it explained somewhere else and then trying to understand the various motivations and intuitions. So what you want to do, trying to remember where it was. So plug that in. Let's get all this on the top. So let's get, and that'll be the next part.